and stuff. And also because this kind of a code is generally made to be employed on project is generally made to be employed on production ready environment in which the date. Yeah, good.
So there is either you should hold the mic a little away from your face, or there is some constant sound.
Hello, can you hello?
Yeah, there is a constant sound. Is that just for me or the others also? Like a fan.
Okay, I'll off the fan. Hello, am I like is it fine now?
Yes. Okay. Yes, that's better.
Yeah.
Okay.
So, and then as I was talking, these kind of models are generally required to be run on production environment in which the data has been coming continuously uh, fed into the system, so that it is very important to make sure that if it is properly scalable, that the detection time should be very low or has to be taken into account. So we'll also talk about that. So first of all, problem statement. So this problem has been introduced just to check whether the in a very like dangerous environments of working outside in a construction site or some factory, so whether the people are wearing their helmet or not. So it's mainly about detecting that, as it is quite evident. So the data set what we have is around 5,000 images we had for training, and 1,766 images we had for testing. So, and there were three labels in the images. One was helmet, head, and person. Person seemed to be a very niche label. It was not present in every image. Like in a very few images, it was present. But we still kept it in the data set to just check like what would be the effect of introduction of a very small category label. Will be able to get a good detection result for the person in the future, in the output model. So the image size are all the same, 416 by 416. But as we can see in the reflect, there was reflection in the images which was actually intentional, because some of the images, as you can see in the left, were like taken in the some were taken in the portrait mode and some were in the landscape mode. So to make them equivalent, they what they did was, instead of padding them with zeros or some other thing, they did a mirror padding. And actually we do have annotations for all the helmets that are uh, in the region of in the reflection region. So there was, as we have discussed earlier, that you asked us whether to remove the reflection. So we thought that it was not necessarily like important to remove the discussion, because we can have more data from less number of images if we actually have the annotations for all these helmets present above. So, but in mostly, like I think 5 to 7% of the images, only 5 to 7% of the images actually contained helmet in the reflections. Yeah, ma'am, you were saying something?
No, I just said okay. I understood. I mean, this you were referring to my suggestion, right?
Yes.
Yeah. Okay.
So, let's first focus on the faster RCNN model architecture. So, this model was actually an improvement on the fast RCNN model, which were actually made for very fast detection purposes and the training purposes. So what happens in this model is it constitutes of two modules. Okay, so one is reason proposal network, which you can see here in the in this left side, and the other one is the same fast RCNN architecture. So reason proposal, like by like as you can see, the reason proposal architecture is again very narrow, like convolution network architecture, which actually gives us the reason which are then fed to the uh, fast RCNN model. So as our main goal for these kind of models is to reduce the computations so that it can become much more faster for training as well as for detection, because they have to be at the end of the day being kept into production, and these are actually suggested by industries, not the theory, not the like theory. So to make it faster, as in earlier in fast RCNN also depended on creating reason, but there was a different architecture that created a reason, that proposed the reason. But in this, we use a common set of convolution layers, so which produces feature maps for us, and those feature maps are directly given to the reason proposal network to give output as a reason that we will see how it's done. So in RPN, what we have, there is a reason, uh, what you say, as you can see, the feature maps have been provided here. So this is a feature map. So we have a sliding window. So that window basically contains one like intermediate output for like complete CNN layer, and then they are sent to the sister two sister layers. One contain one does the classification and one does the regression. So regression part gives us basically the size of the output region. So four coordinates contains the top. So there are it's the dimension is four here. So four is for the first two are the points for the top left corner, and then are width and height. Okay, and the then one is this classification layer. So it just basically gives us the um, whether it's like it's an important object or not. So the one of the main issues in the earlier networks were when like as the image gets passed from one convolution layer to another, so the size and the shape of our object that has to be detected keeps changing. Okay, so to make sure that it becomes translate like invariant, so we it contains like every sliding window is made up of different kind of anchor boxes. So these each every have different, they are made for different sizes and different aspect ratios. So for example, when I get say four coordinate layers, so for each anchor I will get a different coordinate layer, and for each anchor I will get a different score. So that depending on the location of my convolution feature map, I would know that it will be able to train what was the shape and size of the anchor boxes, which earlier, because the shape part earlier was not very concrete in the earlier networks. So then after this after we have found this, the training has been done for the coordinates and the scores for them, they are sent to the fast RNN input layer. So in this layer, we this the convolution feature map layer will also be transmitted in that. So there are basically two input layers for two inputs for that. Now for further convolution layer input, we want our output to be of the same size, regardless of the size of the bounding boxes. Okay, so if the box so if the boxes are very large or very small, we cannot have that the output change according to that. So what we have introduced here is ROI pooling layer. So the author has introduced the ROI pooling layer. So what it does, it fixes the output size. So suppose in the paper they are fixed for 7 cross 7 cross 256. So the windows of 7 cross 7 is fixed. Now according to that, according to my input coordinates, that is input boxes, that is the output of this layer. According to that size, max pooling, the parameters for max pooling will be trained. So the max pooling parameter in this, they are not fixed. So that's why it's called region of interest pooling layer, max pooling layer. Okay, so after the two transfer, so after the convolution, couple of convolutions, these are again sent to two sister convolution layers, in which uh, one of them again does the classification, but now it's not the classification of whether it's a box or not, but the category of the box. So so if in so as we see now in our data set, there are three categories. Either it can be a helmet, it can be a head, or it can be a person. So these, and then one more category is introduced, that is background. So, and most of the like in detection part, most of the image boxes are generated during the background. So uh, yeah, so the classification part takes care of what kind of label it is, and the regression parts again like determines the size of our bounding boxes. So that's how we get the output in this case. So the next model that we are going to talk about is YOLO. So I think Maithresh will take over from for you. Maithresh, hello?
Yeah, one second. Shall I share my screen or okay?
Yeah, I can just keep. You can just
Yeah,
continue.
yeah. So yeah, I'll be talking about YOLO. So YOLO basically means you only look once. The first thing I would like to say about YOLO is it's really fast. It's one of the fastest running, prediction algorithms right now. So it can predict at the rate of 65 frames per second on the COCO data set. And this is very important because if we are trying to run this model in production level environment, we need, like for example, if we take a small camera, like some CCTV camera, then it produces like 30 frames per second. So if we at least take like one frame per second, then we'll have 30 images per 1 minute. And like, and we might have even more cameras, more than 20, 30, 40 cameras, depending on the size of our like environment. So we generally get a lot of images in this setting, and this fast prediction is very useful here. And in coming to the architecture of YOLO, first thing is that every image is basically divided into several blocks, several grids. You might call them grids or cells. So as you can see in this image, this is a classic image that is generally used in explaining YOLO. Uh, yeah, next one. No, Lakshya, next.
Yeah, 1 minute. It's not going down.
Yeah, so each grid uh, basically is attached to a certain number of bounding boxes, or they're also called anchor boxes, as Lakshya was talking about earlier. So, and then each bounding box has 5 components: x, comma y. X, comma y are the center of the bounding box. W is the width, height, h is the height, and we have the confidence levels. So the point is, the center of the center x comma y must be inside the grill to which this bounding box is attached to. So what I mean is, for example, we have a dog here. So the center of the dog is somewhere on the five, like fifth row and second column, right? So the vector associated, the bounding box associated to this dog must be attached to this particular cell, not to any other cell. Like for example, there's a cell in which head exists. So that cell is not the bounding box is not attached to that cell, only to the cell where the center of the object lies. And then the vector looks something like this on your right. So in this vector, we have two bounding boxes, and then PC, the first element PC is basically our confidence level. Bx, By, Bh, and Bw are our bounding box coordinates. C1, C2, C3 are the classes, the prediction probability of our there are 3 classes here, so 3 classes, and then it repeats again at the bottom. So basically, this is a vector which has 2 bounding boxes. We can have, in general, they generally use 5 to 6 bounding boxes per pixel. Per grid, and grid size is generally 7x7. And so yeah, so we have a lot of these vectors. Like each this vector is
So you
present for
mean this
each.
is per cell in the grid?
Yes, ma'am. This is per cell. So all these vectors are stacked against each other. So that would be our final prediction, uh, which comes out of our neural network. Yeah. So next. So yeah, after we predict, generally, as we said before, there are several bounding boxes per grid. So if we plot all the bounding boxes, it looks something like this, which look, on your left. So it's very messy, and we don't need that many boxes anyways. So here we need only 3 bounding boxes for 3 images. So dog, cycle and car. So what we do is we do something called as non-max operation. This is performed even on fast RCMM. Uh, but one thing I would like to point out is when YOLO came along the scene, it was in around 2015. At that point, the most of the architectures were the reason why they are slow was they used to find this region of interest and send this region of interest to a neural network each at a time. I mean, we need to run the neural network several times to predict. I mean, we need to run the network for each region and interest separately. The advantage here is we just send the image to one single neural network and then we get the bonding axis. That's it. That's one single shot. So to perform non-max separation, there are several steps. So next slide. Yeah. So basically, it's quite simple. So let me explain it with an example. So here on your right, there are two objects like a human and a dog. So first thing is that we pick a box which has highest probability. So here it is the dog. It has 90% probability. So we pick that box, and then after picking it, we calculate IOU of all the remaining boxes with this particular the box we pick, and then we remove all the boxes whose IOU with respect to our picked box is less than zero point 0.5. So all those images are left. If we do that, sorry, I think green one is the highest. Sorry. So if it is green one, 98%, and then if you pick this green, then the red box goes away. And this 82% yellow box also goes away. Yeah. So just take 1 second. Yeah. Hello.
Yeah.
You don't change the slide. 1 second. So once we pick this 98%, this red box and yellow box are gone. After that, the next highest I mean probability would be the person, 96% here. So we go here to this green box of the person, and then once we do that, the IOU of we'll try to calculate IOU of 96% for green box with red box and yellow box of the person, and then if the so actually it has to be greater than 0.5. It's a mistake. So if it is greater than 0.5, then this yellow and red are removed. So we end up with finally two green boxes of dog 98% and person 96%. So we have also trained SSD for our data set. We'll also talk about the results now. So SSD also quite similar to YOLO, but the only difference is the neural networks convolution layers are little different, and also in SSD there are multiple bonding boxes per single pixel. Single pixel is associated with multiple bonding boxes. Here in YOLO, we divide the region into several grids. So there will be like huge number of bonding boxes which are overlapping in the case of SSD. It doesn't happen that much in YOLO. And yeah, and so let us talk about the results. So in our data set, this is a result for fast RCMM inception. So now on your left is the confusion matrix. First thing we can say is that the precision is quite high, 0.98. However,
Mind, can you emphasize, like,
hello.
yeah, can you zoom in slide, please? Time. This is good. This is with RCM
I don't know.
at
How,
0.5. Okay.
how do I zoom in?
I'm not sure. I think
No, this is fine. Okay, I can. So at
How do I
threshold
remove
of
this thing now?
0.5, you have these numbers. Yeah, this is quite good.
okay.
Ma'am,
Yes.
but the thing is, we have trained the model for 25,000 epochs.
Huh? 25,000?
Epochs.
25,000 epochs.
Yeah.
Oh, wow.
And it took us several hours, I think.
Yeah.
Yes. So why 25,000?
Huh, because we were actually like we were not afraid of overfitting in the form key. The model is like it's coded such that it will always take the best model with respect to regularization loss. So we thought that like the because when I was looking for the default values for the epoch, then for the faster RCN and inception itself, they were training for 100,000 epochs in some places. Not exactly for this data set, for different data sets, but when we were like we are also doing some like internship work in our company, we have seen that the most of the problems that occurs is that we are not able to detect very small images that will come to later in the final visualization of the results. So to get those images also, we were trying to give more training to the data set.
Yeah. So even after doing 25,000, we still have some issues here. For example,
Recall.
confusion matrix. When there is a helmet,
Background and helmet.
yeah, exactly. So helmet goes into background, and sometimes head also goes into the background. And the accuracy for person is really low, like it's almost negligible. I mean, the main reason is that the images in which the person is there, it's there like only 100 or something, and then the way the person is annotated is quite weird. I mean, for example, sometimes only hand is there, sometimes the leg is there, sometimes half the body is present. So such things it was quite difficult to predict those things. I mean, uh,
Yes, in your training data set, if it's not
Yeah.
yeah,
Plus the thing is for threshold in the detection result, like confidence interval is also zero point 0.5, and the threshold for IOU is also 0.5. So the classification, so the result that we see are filtered out according to that.
and the second one.
Yeah. So this is the SSD mobile net. So as you can see, it has even better precision, that is 99%, but the recall is 0.037. So the thing is, most of the thing, as you can see here, like most of the data is actually going into the background. So if it is classifying 100 images as a helmet, so 99% it is correct. Yeah, that is helmet. But the thing is, it is not able to classify around 1400 images at the same time.
I mean, when there's a helmet, it doesn't always say that it's helmet. It goes into
That's a yeah.
like, similarly with head also. I mean, so
Yeah. But when it says it's helmet, it's 99% time correct that it is helmet.
yeah,
The best result we get is for YOLO 5.
Ulofsec gives a very good result. And here, if we look at the precision is little lesser. I mean, on the right, 0.93. However, but the amount of images of element that goes into background are very less. Like, so the similar thing happens to head, but it has slightly higher accuracy for predicting person compared to the previous models. But still, it's not very. I mean, it's not good at all, and it's very low. Uh, so now we will all these images, as Lakshya was saying, they are all taken at 0.5 IOU. That was the threshold with it, and we tried to reduce the threshold also. We tried to do it for 0.23, and we were getting worse results than what we are showing now. So uh, yeah. So next.
So this is the speed for detection that we have. So okay, this is the training that needs to be changed. But for prediction time, YOLO V5 like can predict for 59.2 images per second. The same thing mobile net SSD mobile net does, like it can predict 26 images per second. But the faster RCN and inception, it only does 2.81 images per second. So in most of the cases, when we see in the production environment for detection, YOLO V5 is actually being preferred over all the other model networks.
Yeah, it is roughly twice as fast as SSD, and for this particular size, I mean 416 cross 416, it could be a little slower for other sizes. uh,
So and the but the training time per epoch, when we talk about, I think for YOLO V5 it was 4 minutes. Let me copy paste.
slightly less than 4 minutes.
Slightly less than 4 minutes, and for per epoch. While for SSD mobile net it was 0.3 seconds per epoch. So we thought that we can actually go for quite a like bit more epochs, and to make sure that the results were consistent with each other, we went for FR like RCNN inception model. Like even though it takes 1.3 second per epoch, like we went for the same number of uh, epochs for both the models.
Yeah, one more thing is that we trained YOLO V5 for only like 50 epochs, and the result is still better than all the other SSD and FRCM. Like,
Yeah, so that was going to be my next question. Like, after some number of epochs, you will see very little improvement.
Yeah.
hello, ma'am?
You didn't decide some threshold beyond a certain, or you just decided to go 25.
No, actually, like the thing is that the threshold for gain like of change in what do you say, the error was actually given very we gave it very low, because first we tried for only 100 or 200 epochs. Then we saw that the time was actually very like time per epoch was quite low. So so we thought that we can give it a longer time, plus we already have that after like every, I think, 1,000 epochs or something, after every 1,000 epochs it actually saves the what do you say, uh,
Model.
model. So if we so at the end of the completion, it will always save the best model that it has saved earlier. So that's why we thought that it was never a bad idea to go for better result, because we wanted to check that how much better can we get with time
Okay.
if given it more resources.
And this was this is on CPU, right? This is on your
On GPU.
Collab.
on GPU. Oh,
Yeah.
which so CMI GPU or some other?
No, it's on Colab GPU.
Okay.
Colab
All right.
GPU. So in terms of memory uses, while training, faster RCNN takes about 4 times more GPU than SSD mobile net. So even the resources are being taken more by the inception compared to mobile net.
And YOLO will require lesser.
Yeah, and YOLO, the network is also quite similar. I mean, compared to the others, and the size wise. Like,
The one of the main reason was because we got very good result for YOLO 5 for a very few epochs. So we wanted to match that result with the others too also. So we kept going with it.
Okay.
So the visualization of the prediction. So as you can see in these images, so first image is for uh, this fast RCNN, second is for SSD, and the third is for YOLO V5. So so as you can see that it is able to tell that it's helmet with a better probability than the others. Faster RCNN. Okay, but at the same time, so these kind of helmets which are very far away, which are very small and not much contrast is present in them, it's not able to detect them, while YOLO V5 does a quite decent job in it. Because as you can see, the probability falls very quickly as it goes back. So even though it was very high, 95% here, it went to 54% here, but it went from 81% to just 63%. So it is like it confidence falls much like linearly in the YOLO V5 case, but in faster RCNN and SSD, they fall rapidly to the point like exponentially, and like there is absolutely no confidence in the result we have. So what we try to do when we try to reduce the confidence threshold, so in that case we started getting some like weird result also for other places which were not exactly objects. So that's why we have to keep it at 0.5.
So in the top three images, none of them has detected the person, right? Person
yeah,
or head.
Yeah. None of them.
the label should be head. I mean, he is not wearing a helmet. I think.
Hmm.
So, yeah, it's since
But you also
the
have a person, so at least I mean, more features of the person are visible there. So
Yeah.
this
Ma'am,
person,
actually, the person is detected when we reduce it to less than confidence is reduced to less than 10%.
I see. Okay.
Yeah. So, for example, in this case, there are quite a few people, and here too. But so faster RCNN does again, like the confidence again falls very rapidly here, and it's only able to get like 2%. It's this one, like this helmet is detected with the efficiency confidence level of 99%, while these others are not even detected. And in this case, the one it is detected is like 100%, and the other it does not say anything about them. So, but in this case, it detects them. I'm not sure how it's detecting this helmet there.
Actually, there's no helmet there. I think
So
it's
there is no helmet there, but
There is a helmet on the lower.
yeah, there is
Yeah.
helmet there, but it's not able to detect.
But on the upper image, it does a pretty.
Yeah, in upper image does a pretty good job of detecting helmet.
no, actually these images are the complex images. I mean, the images where we thought things are not going very well. I mean, we specifically choose these images to show.
Yeah,
No, that is a good thing because these are the kind of images you'll probably see in real life.
yeah,
Also, not necessarily such good resolution.
yeah. So we have actually chosen the images in which like it is very difficult to determine the uh, edges of the helmets and those kind of stuff. So so these grids do a pretty like good job of hiding those edges in this case. So it's not able to detect this helmet here, but the YOLO still able to get the worst of it. And same. So if there is like a normal kind of image, this, this was like really shocking when we checked it out. That because of the background is yellow in this case, it is not able to detect a very obvious helmet here.
Mm.
So this is the SSD case. Faster RCNN and YOLO V5 are able to detect those helmets.
Yeah, so SSD does rather poorly in all the images.
Yeah.
Mm. Yeah, and another interesting thing in the bottom image is the person whose head is not detected. She's wearing a helmet. I mean, uh, so I mean, neither a head is detected nor helmet is detected in the
Yeah.
left two images. YOLO still detects this as a helmet on the right.
Yeah.
I think the color of the hair and the helmet
Yes,
kind of.
in fact, I mean, even I couldn't recognize the shape.
Yeah.
Yeah, good.
So these are the references.